One of the subjects that fascinated both Graham and Agnijo was Ramsey theory. This was a relatively new field that had been pioneered by English mathematician and philosopher Frank Ramsey, brother of Michael Ramsey, who became Archbishop of Canterbury. Frank Ramsey graduated in 1923 as senior wrangler, top of his class, in mathematics at Trinity College, Cambridge, where one of the authors, Agnijo, was no student. At the age of 19, he learned German. In less than a year that he produced the first English translation of Wittgenstein's monumental work Tractatus Logico-Philosophicus, the goal of which is to explore the relationship between language and reality and define the limits of science. Subsequently, Ramsey was instrumental in persuading Wittgenstein to resume his philosophical research and at the same time come back to Cambridge where he previously taught. In 1928, aged 25, a little over a year before he died following an abdominal operation, Ramsey wrote a paper called On a Problem of Formal Logic. The main aim of the paper was to solve an aspect of what mathematicians call the Entscheidungs problem, German from decision problem, proposed by David Hilbert and fellow German mathematician Wilhelm Ackermann. This asks whether a step-by-step method always exists for deciding whether a given statement can be proved from basic starting assumptions or axioms using the rules of logic. Along the way to the main conclusion of his paper, Ramsey believed that at the time seemed like a fairly minor result but which turned out to be of fundamental importance. It is now known as Ramsey theorem. It's the simplest illustration of it. Of the simple illustration of it is called the theorem of friends and strangers. Suppose there are 6 people at a party. If you consider any two of them, either they've met before, in which case we'll call them friends, or never been met, or they've never met before, and so are strangers. Figure 5.2 shows an example. Alice had met has met Bob before, so that they're friends. However, Alice and Kelly haven't previously met, and so are strangers. The theorem of friends and strangers states that among six partygoers, either at least three will be mutual strangers, none of them having met or other two before, or at least three will be mutual friends. In the case illustrated here, Alice, Bob, and Don, for example, are mutual friends because each one of them has met the other two. In other words, they're pairwise mutual friends. No matter how you draw the connections, you'll always find at least one such triangle of pairwise mutual friends or pairwise mutual strangers. Ramsey theorem in its original form. You won't be astonished to learn isn't framed in terms of people at parties. Instead, it focuses its attention on the more abstract and general subject of graph theory. Everyone's familiar with the type of graph that show how one quantity varies with another, curve or straight line, plots of x against y, that, that we learn about in school. However, graph theory deals with graphs a, a completely different kind. Graph theory belongs to a branch of maths known as discrete mathematics, and the objects it studies don't vary smoothly but instead take on distinct discrete values. The graphs in the graph theory consist of points, also known as nodes or vertices, any one of which may be connected to one or more other vertices by lines or edges. These graphs come in different types: directed, those with arrows on the edges; undirected, complete, finite, weighted, and so on. A complete graph is one in which every pair of vertices is connected by a unique edge. Graphs may also be labeled, for example by coloring the vertices or edges. Another important concept in graph theory is the clique. A clique is a subset of vertices distinguished by the fact that every two distinct vertices in a particular clique are adjacent. Ramsey theorem has to do specifically with complete graphs that have colored edges. It says that in any complete graph with colored edges, it's always possible to find cliques of the same color providing the graph is large enough. That may seem like a pretty obscure piece of information, but it turned out to be the seed from which sprang an entirely new branch of mathematics, Ramsey theory. The overarching, the overarching idea in Ramsey theory is that, however the system may appear to be, provided that it's sufficiently large, it must contain some order. A typical problem in it runs along the lines: how many elements of a structure are needed to guarantee that a particular property will hold. In 1971, Ron Graham and a colleague, Bruce Rothschild, published a paper on Ramsey theory that had to do with cubes, and not just the common or garden variety, but cubes in any number of dimensions, hypercubes that might have a dimensionality of 4, 5 or more. Everyday cubes, like sugar cubes or dice, are 3D shapes and have to the 3 equals 8 corners equals x corner of vertices. A 4D cube, sometimes referred to as a tesseract, can be properly visualized because we think only in 3 dimensions, but can be shown mathematically to have 2 to the 4 equals 16 vertices. A 5D hypercube has to the 5 equals 32 vertices, and in general an n-dimensional cube has 2 to the n vertices. Think about an ordinary 3D cube and connect every vector to each other's outer vectors by a line. There will be 28 lines in all as shown in figure 5.5. Now let's color each of the lines red or blue in any way we like. In the illustrations here, dark gray represents blue and light gray represents red. One of the many possibilities we may end up with is shown in figure 5.6. Now let's hear the questions. Hear the question. No matter how we decide to color the lines, is it always possible to find 4 vertices in the same plane so that all the lines connecting them are the same color? In the graph of the cube we've just colored, there are indeed 4 such vertices as shown in figure 5.7. But if instead we decided to color the bottom edge in figure 5.6 blue, dark gray, there wouldn't have been any set of 4 vertices that satisfied our criterion. Having found a contact sample, we know that in 3 dimensions at least, cubes can be can meet the conditions of our problem. In their 1971 paper, Graham and Rothschild asked a generalist form of the question we've just talked about. Connect each and every pair of vertices of an n-dimensional hypercube, they said, to make a complete graph having 2 to n vertices. Color each of the edges red or blue is the any dimensionality of hypercube so that among all the possible colorings at least one must give rise to a complete subgraph of 4 coplanar vertices. A complete subgraph is just a complete graph that forms part of a larger complete graph. As in the case of figure 5.7, the answer they found yes, provided the dimension n is large enough. It's guaranteed that no matter how the vertices of the hypercube are colored, there always be a slice of subgraph. There always be a slice of subgraph that has single color. Graham and Rothschild weren't able to determine the smallest value of n that would force the conditions of the problem to be met. In fact, no one's yet done that. However, they were able to show that the minimum value it could be was 6 and the maximum value, the upper bound, was stupendously large number, which in the simplified form has come to be known as Graham number. You might think there's a pretty major uncertainty, knowing only that the value of something is between 6 and number that's inconceivably vast, and you'd be right. But the wide uncertainty is due to incompetence of the mathematicians involved, but instead the incredible complexity of many problems in Ramsey theory. We didn't look any further than the friends and strangers at a party scenario considered earlier to get a sense of the difficulties faced. Remember, we said that you'd need a group of 6 people to ensure that there be 3 parents of 3 strangers. In the notation of Ramsey theory, this can be written as R3.3 equals 6, where R3.3 is called Ramsey number. In general, the Ramsey number M.n gives the minimum number of guests who must be invited to a party to guarantee that at least M will know each other or at least N will be strangers. It's known that R4.4 equals 18, but beyond that, things get a bit hazy. The trouble is that the number of possible combinations in Ramsey theory grows explosively fast with the size of problem. A graph representing 4 people and the possible pairwise connections between them has just 6 edges, and 2 to the 6 equals 64 possible red or blue red or stranger colorings. But the graph for 6 people have 15 edges, and 2 to the 15 equals 32,768 ways of being colored. Mathematicians have yet to figure out the value of R5.5. In other words, the size of party you'd need to ensure that at least 5 people will be acquainted or 5 will be strangers. The answers, known to be between 43 and 49, and is strongly suspected of being 43, and no one's yet been able to prove it. The brute force method of checking all the possible ways of coloring a graph of 40 people with 2 different colors is a non-starter. Such a graph has such a graph has 903 edges, and therefore 2 to the 903 possible ways of being labeled using 2 colors. a number of facts exceeding in a number of facts exceeding the number of subatomic particles in the observable universe than the capacity of any computer to check case by case. The problem investigated by Graham and Rothschild is similar in nature to that of the friends and strangers situations we've looked at, but involves a lot more practices and edges. Any possibility of checking individually all the different ways of coloring the connections between vertices of multidimensional hypercubes is out of the question. Instead, mathematicians had to seek other, subtle methods of proving if and when a particular condition is met, and in the case of Graham's number, this often succeeds only in establishing bounds for the solution of problem rather than the solution itself. Graham's number, as we're going to find out, is so spectacularly large that it doesn't seem like a very useful upper bound, especially when the actual answer to the problem it addresses is suspected of being almost comically small, possibly in the teens. But the fact is at start. The same was true of Schiff's number. It, too, was stated as an upper bound of problem and is a large number, although not in the same league as Graham's number. It served as a starting point for other mathematicians to the to try to narrow the gap between the known upper bound and the actual solution. More recently, progress involving upper bounds has been made on a big open question that was first proposed in 1846 by French mathematician Alphonse de Polignac, though doubtless others had thought about it before. The twin primes conjecture, or Polignac conjecture, asserts that there are infinitely many pairs of prime numbers that differ by only two, such as 11 and 13, 29 and 31, 100 and 101 and 103. Is a claim that's easy to understand and almost universally believed to be true, but is stubbornly resistant to proof. Some progress was achieved in 2004 when American mathematician Daniel Goldstone and Turkish mathematician Cem Yildirim showed that by making certain assumptions, including the truth of another unproven conjecture known as the Elliott-Halbergstam conjecture, there were infinitely many prime pairs that differed by just 16. A flaw in the proof was corrected the following year with help of Hungarian mathematician János Pence. Then, out the blue in 2013, a Chinese-born mathematician and Chinese-born American professor at the University of New Hampshire, Yitang Zhang, made a startling announcement. She established, without the need to make any other assumptions at all, the first finite bound on the least gap between consecutive primes that is attained infinitely often. His proof showed, unconditionally, that there are infinitely many pairs of prime numbers that differ by 70 million or less. Obviously, 70 million is slightly more than 2, but the point is that the point is that Zhang had shown a way for other mathematicians to make further progress on the conjecture. In 2014, using Zhang's approach, the upper bound was less to 246, or if a generalized form of the Elliott-Halberstam conjecture is assumed, as low as 6. Refinements have also been made to the upper bound that Graham's number describes, as we'll see. But for that moment, let's focus on trying to comprehend the sheer scale of this number and the extent to which it outshines every other star in the numerical firmament that we've come across so far. It was in conversation with Martin Gardner, one of the greatest writers on popular mathematics, that Ron Graham gave a simplified explanation of the number named after him. The original Graham's number was explicitly identified in 1971 paper, and its description this would have been too difficult for non-mathematicians to follow. Effectively, Graham invented a new number by a relatively easy-to-follow method that gave a feel for the enormous size of the original. This invented number was not only specific but was actually larger than the original, so that it truly was an upper bound to the solution of Graham and Rothschild's problem. Gardner then made the new issue to understand Graham's number the subject of his Monday column in the November 1977 issue of Scientific American. 3 years later, it won even more public fame with an entry in the Guinness Book of Records for being the largest number at the time ever used in mathematical proof. Graham's new number is nothing a power more than a power tower of 3s. In other words, is 3 to the 3 to the 3 to the 3 and so on. Written as a repeated exponential, it looks like this. Where the dots stands for dots of 3s. In fact, a power tower of 3s so high that it's impossible to imagine. Even if the trees were microscopic in size, the tower would rise above the half Mount Everest, and then on and on, far beyond the extent of the observable universe. We have to accept from the outset that we can never ever truly grasp the size of Graham's number. All we can do is try to follow how it comes about. The first step in reaching Graham's number is to think of the number 3 is to think the number. Remember for the last chapter that the one up arrow on its own represents exponentiations, so that 3 up arrows 3 equals 3 to the 3. 2 up arrows represent the next rung up the hyperoperator ladder, tetration or repeated exponentiation. Already we've gone past 7 trillion. Next up is pentation, giving us a power tower that's 7.6 trillion trees high. If we were to print this out, replacing the dots with the correct number of trees, and assuming that each tree was 3 millimeters high and would stretch about 23 million kilometers into space. That's more than half the distance to Venus at its closest approach to Earth, so we might call this number the Venus Tower. Now, add another upper row. This takes us up to the level of hexation. Notice that inside the right-hand set of brackets is our Venus Tower, a stack of trees that would reach over halfway to the nearest planet. So we can write. What does this mean? Pentation. Shown by 3 up arrows is repeated rotation, so that now we're dealing with not just a Venus power tower of trees, but a Venus power tower of repeated rotations. If we represent this vertically rather than horizontally, it looks like. Duplicate To be clear, this means taking the number of 3, then taking a power tau of 3 of height 3 to get roughly 7.6 trillion, then taking this result and making it hex and making it the height of a power tower of 3 to get the Venus tower, then taking this result and making it the height of power tower of 3 to get something vastly large, and repeating the whole process a Venus tower number of times. There's no point in worrying on your neurons then to guess how big the result will be. You can't. No, no one can. You might just be able to picture in your mind's eye flying in spaceship more than half the way to Venus and seeing through the window all those teeny trees marching across millions of kilometers of space and forming a power tower. If you want to wrap your brain around the number 3 Venus tower, you have to picture each of those little trees being replaced by a power tower of trees. So we arrive at the first step along the way to Graham's number. Following the line of John Graham and Martin Gardner, let's call this number G1. Of course, shockingly big in terms of anything the physical cosmos has to offer. But here's the thing: in the next step along the roads to Graham's number, the brain-bustingly last number G1 becomes merely the number of apparatus used in defining a far larger number G2. And before you get comfortable with that idea, G2 is a number of apparatus in the definition of an even larger entity, G3. On and on this insanity continues until finally we reach G64, which is Graham's number. Each G number serves to specify how many apparatus are needed to represent the next G number in the series, all the way up to G64. The growth rate of the G numbers is outstanding, incomprehensible. Graham's number itself is so large that, in comparison, Squire's number and even Moser number are utterly insignificant. The speed at which numbers grow from one to the next, and the ease with which, at a few dozen steps, we can arrive at something of the monstrous scale of G64 is testimony to the power of a process that we're going to see a lot more in the chapters and head recursion. Graham's number came about as an easier to digest version of the smallest known upper bound to the solution of the geometric Ramsey problem we talked about earlier, but in the years since it became famous, it been replaced in that role by successively smaller numbers. A 2014 paper by Mikhail Lavrov, Mitchell Lee, and John Mackey gave a new upper bound of 2 to about 6, which is still a big number, too ridiculously small compared to G64. 5 years later, Eric Lipka reduced the upper bound still further to about 5. The true solution of the problem is thought to be very small indeed and probably close to the currently known lower bound, which, according to an online preprint submitted to Cornell's arXiv website in 2008, is 13. We've seen that there is nowhere near enough room or matter in the observable universe to be able to write out in full some of the big name numbers that we've already come across: the googolplex, Squire's number, Moser number, and so on. So obviously, there's no chance that there ever be a complete digital representation of Graham's number, even if we knew all of its digits, which we never will, and even if every single plank followed in the known universe were devoted to the task. But it's more than that. If you think about the googolplex, it's impossible to write out in full, but it's easy to write out in full how many digits it contains, just one followed by 100 zeros. In the case of Graham's number, or the observable universe isn't big enough to hold even this number of digits in the digital representation. Nor is it big enough to represent the number of digits representing the numbers of digits in digital representation, and so on for a few dozen more embeddings. A few dozen more such embeddings. We'll never be able to see Graham's number in full nor know what the vast bulk of its digits are, but we can at least console ourselves by seeing how it ends. You may have noticed that not operas have made their mark in Graham's number, formidable as this system of notation is compared with more familiar forms such as indices and power tables. It doesn't cope well with the kind of numerical giants we encountered once recursion take hold. In the case of Graham's number, we ended up we ended up using rows of dots to indicate where there were far too many operas to write out in full. Fortunately, other ways of representing big numbers have been devised that can take over when operas are overrun.